here we are, section 7.1, using the fundamental identities. If I were you, I wouldn't write this down because you've already written it down and you have access to it. But I wanted to remind ourselves of it. And what I want to just quickly look at, if we look at the reciprocal identities. The reciprocal identities, you can actually think of each one in multiple ways. So we know that sine and cosecant are reciprocal functions of each other. But that means you can think of sine as 1 over cosecant, or cosecant as 1 over sine, or anytime you multiply reciprocals together, you always get 1. So with the reciprocal identities, there's actually kind of like 9 forms of them. There's only really 3 you have to memorize, but what I'm trying to get across here is that by knowing this first one that I highlighted, everything below is implied. And then the same thing with the Pythagorean identities. There's really 3 Pythagorean identities, but once you know this one, there's some other forms of it, and these are useful forms. So again, once you know the top one, the ones below are implied, but just kind of keep that in mind when we're using these identities. We've already derived them in the past, so I'm not going to take time to derive them here. If you have any questions, you can feel free to stick around after class when we have study hall. But we've already derived them, like I said. The quotient identities, I mean, yeah, we could have other ways of rewriting them, but honestly with these, we typically just stick with these forms. The cofunction identities are ones that always seem to trick students up. And it's funny because, like, a lot of students are like, how do I know when to use them? They're just so weird looking. But they're really obvious to spot. Remember, pi over 2 is the same as 90 degrees. So most often when you're going to use the cofunction identities, you see them written. They're the only ones where the angle is 90 degrees minus the angle, or pi over 2 minus the angle. Like, that's the only time that you're ever going to use those identity, or the only identity you'll use when you see that. So it's pretty obvious. It's also the only identity where the angle actually changes. If x, we'll deal with degrees because it's a little easier to think about. If x is 40 degrees, 90 degrees minus 40 is 50. So you'll have 40 degrees here and 50 degrees here. It's the only identity where the angles change completely like that. So it's another way to spot you're going to use cofunction identities. And then even and odd, these are new. So these you might want to write down, but there's not much to know about them. And remember, with even and odd functions, when we did those last semester, we could use symmetry of the graph. So graphs that were symmetrical about the y-axis, those are even functions. And if you think about our graphs here, and actually I'll just very quickly. So sine does this, that's sine. Ooh, that's a really horrible sketch, but we'll go with it. And then cosine has the cups on either side. And then tangent, oh, that's really bad. But hopefully it'll be enough for us to work with it. You can use a graphs to determine if they're even or odd. Cosine's the only one that's symmetrical to the y-axis. So cosine is an even function. Sine and tangent are both symmetrical to the origin, and remember that means you can rotate them 90 degrees or 180 degrees. Just turn your paper upside down and the graph will look identical. So sine and tangent are odd. And then the corresponding reciprocal identities will have the same parity. So if sine is odd, cosecant is also odd. If cosine is even, secant's also even. And if tangent is odd, cotangent's also odd. And the thing to remember about even and odd functions, f of negative x is negative f of x. But even functions, f of negative x is f of x. And so that's why they're called even odd identities, and that's where they come from, is from the symmetry of the graph. So, any questions about any of the identities? Because now we're just going to have a whole bunch of examples. Yay! We're going to do some together. I'm going to give some to you to try on your own. It's going to be a big identity party. Yeah. All right. And in case I forgot to mention, it's really going to be helpful if you memorize these. If you don't have them memorized, though, seriously, it will help for today's lesson if you have access to these identities easily. So I didn't really give you time to write them down right now. You can, here actually, no, I don't want to because the answers are posted. But if you go into the Unit 6 in Canvas, the Unit 6 module, that was the module at the bottom where I put links to the sheet with all the identities, module 6. So if you want them. Anyway, with that said, so what are we going to do with them this section? This section is going to be about using them to simplify expressions. It's really the focus. And so if we look at this one together, basically I'm going to do an example together, give you one to try. We'll do another example together, give you one to try, and so on. So let's do this one together. So use identities to find the value of the other trig functions given. And we've actually done problems like this before in previous units, but let's just kind of quickly remind ourselves. So the idea is they've given us cotangent and sine. We're going to find the other 4 trig functions. Now we could draw a triangle, but because the focus of this unit or this section is using identities, let's go ahead and use identities. And sorry, somebody actually wanted me to scroll up to take a picture. So I'll scroll up here if you want to take a picture of these, and then once I do that, I'll scroll down to get the other chunk. So that's a good idea. Thank you to the person that suggested that. So hopefully you guys got a screenshot of that one. And there's the bottom part if you want to get a screenshot of that. All right. So there's different ways to do this, and you know, a lot of times you have a choice of identities to use, but I personally think on these problems, the easiest, I mean, if we look at this list, the reciprocal identities are definitely the easiest. You just flip a fraction. The next simplest looking ones, just based on the equation, are these quotient identities. And most of the stuff, you can usually just use those 2 identities on these types of problems. So let's take a look. It just kind of depends on what they give you. So if we use the reciprocal identities first. So we know that we're given cotangent, and we know that tangent. Oh, by the way, this is a new Greek letter too. You're going to see this in your homework, so I put that there. This is the Greek letter. It's funny because it depends on who you talk to. Most people say phi. I met a man who was actually Greek, and he said phi. I don't know if there's different dialects or different accents in Greece. Maybe sometimes they say phi, sometimes they say phi. I don't know. But since he said phi, I say phi. But you will hear most people say phi. So anyway, we know that tangent of phi is 1 over cotangent of phi because they're reciprocals. Therefore, we know that tangent is going to be the reciprocal of -3, so it's going to be -1/3. Boom, one done already. And the other one we're given is sine, and we know that cosecant of phi is the reciprocal of sine of phi, so that means that cosecant is 10 over root 10. Oh man, we gotta rationalize the denominator. So we'll multiply by top and bottom by root 10. Ooh, I forgot my c. So then we'll get cosecant of phi is 10 root 10 over 10, so it looks like root 10 simplified. Now that's as far as we can go with reciprocal identities. Let's see what we can do with quotient identities. Quotient. Well, we do know that tangent is sine over cosine. And by the way, when you're doing your homework tonight, I would really, really recommend doing exactly what I'm doing here. I'm writing down the identity first and then plugging into the identity, because writing down the identities is going to help you memorize these better. And I don't know, I heard somewhere that memorizing these things is going to be helpful. Somebody wants to know how you would tell the symbol from the no solution symbol. And I will confess, this is actually one of the reasons why I stay away from the no solution symbol, because I can never keep them straight. One of them is more straight up and down, more vertical. One of them is more slanted. There's this, and some people do this. That's just nonsense. Don't even do that. I believe, and this is just me guessing, I'd have to look it up. I believe that this one, the first one, that's more vertical, is technically the symbol for phi. However, in math, it's kind of a standard anytime you use a variable. I don't know if you've ever noticed this in textbooks, and I try to do it too when I'm typing, because it is the standard. Anytime you're putting a variable, the variable should be in italics. And then when you put things in italics, they kind of slant. So when you see phi written in the textbook, it actually looks a little slanted. So like I said, I believe phi, when it's just printed without italicized, I think it is straight up and down, and then the slanted one, but it's definitely at a very dramatic angle. That this second one is the no solution. I can't remember though. It's a good question, but I just have to look it up. Somebody says in Google it shows that the line is straight. Are you saying the line is straight for phi? Okay. So yeah, so what I'm remembering is right. So phi technically is straight up and down. It's just we always italicize it when we're doing it when it's typed. And so I just always slant it a little bit too. But the no solution symbol is definitely much more angled. So good question. I wish I had a better answer, but hopefully that gives you something to go on. I don't remember what we were on, but we'll just finish this up with the tangent thing here. So we've got cotangent, sine, tangent, and cosecant. We're missing cosine and secant, but there is a cosine in here. So I'm going to go ahead and solve this for cosine, and then we can plug in. You could plug in and then solve for cosine. It doesn't matter which order. So if I multiply both sides by cosine, I'm going to get, not that, I'm going to get cosine tan equals sine, and then we can divide. So, so that's what cosine is. So then, now I can plug in because I have sine and I have tangent. So cosine is root 10 over 10 over tangent, which is negative 1 over 3. Dividing by a fraction. No big deal. We're going to multiply by the reciprocal. And so now we know cosine is negative 3 root 10 over 10. Yay! And then finally we can go back to our reciprocal identities. Reciprocal. And we know that secant is the reciprocal of cosine. So secant is negative 10 over 3 root 10. Oh, we should rationalize again. So we're going to have this 10 on top that's going to cancel out with the root 10 times root 10 at the bottom. So we'll have negative root 10 over 3. Yay! So, any questions about that? That is one way we can use the identities. Does anybody need more time writing this down? All right, I think I didn't see anybody. So here's one for you to try. Give that one a go. I'll give you a main thing. It's not hard, it just takes a lot of writing. So let's go 2 minutes. and then we'll come back. All right, so let's take a look. Whoops. And here is a solution. Honestly, there's more than one way to do these. I think this is probably the most straightforward. Like I said, I like to do the reciprocal identities first and just get as many as I can done that way because they're just so easy. Then I do the quotient identities because I think those are the next easiest identities to work with. If I have to, I'll go to the Pythagorean identities as a last resort. But I try to avoid those if possible. Any questions on this now that you see it? Yes. Well, it actually is. It's a little harder to do an italics theta when you're handwriting, but if you do look back at the book, you'll see the theta is just slanted a tiny bit. You're right. And again, it just has to do with it's hard to do italics. I mean, we'd have to be really precise about making sure when we're not doing an italics theta that it's straight up and down. And then when we want one, we have to make it more angled. But when we're handwriting, I mean, it's just, it's so, I mean, that whether it's italicized or not, that line in the middle of theta is still always horizontal. And that's the easiest thing to indicate a slant. That's why with phi, because that line is vertical instead, it's a lot easier when you're handwriting. I don't want, it's kind of, we don't slow down our handwriting to do it. So, but you're right. Fair point. Very fair. And even like with the X, how are we going to make an italics X when we're handwriting? How do we show that? It's a little hard. And the Y, yeah. So we usually when we handwrite, we don't worry about the italics. And you will see, honestly, with the phi that some people don't. Some people will just do it the straight up and down because of that. But that one's an easy one to show, so fair point, fair point. So somebody asked in the chat how I knew to come back to the reciprocal identities, and I didn't have to. So I used the reciprocals as much as I could. I got sine and cotangent. Then I went to the quotient identities to get cosine. The last one I had to find was secant. Now, at that point, just to show you what it would look like, because we don't have an example, I could have done the Pythagorean identities. And I do this all the time. Identities. When I write it, identities. That's how I always do it. Let me fix that. Identities. Anyway, I'm trying to find secant, and if you go to the Pythagorean identities, the one with secant looks like this. 1 plus tangent squared theta equals secant squared theta. So we could. There it is, 3/4. So 1 plus 3/4 squared equals secant squared theta. And 3/4 squared would be 9/16. To add these, I need a common denominator, so I'm going to rewrite the 1 as 16/16. So then I get 25/16. And then I take the square root, and I get 5/4 is secant theta. And I would have to be a little careful also, because if I took the square root, I could get a plus or a minus. But going back up here, if cosecant is positive, then we know sine is already positive. So if sine and tangent are positive, all students take children, we'd have to be in quadrant 1, where cosine is positive. Therefore, our secant's also positive. So the other problem with the Pythagorean identities is you got to worry about your positive or negative sign. So you'd have to go back and think about that. So Pythagorean identities work, but this is why I like to use them as a last resort, because they're just so much more complicated than the reciprocal identities. Yay! So almost always you'll be able to do reciprocal quotient and maybe have to go back to reciprocal. But sometimes you're going to be stuck. You're going to have to use a Pythagorean. So yes, it's just a preference to do the least amount of work. So any questions about that? All right. So then we have stuff like this. Simplify. Now, like I said, we're going to do this one together, and then I'll give you one to try on your own. So when it says simplify, I'm going to ask you to please show your work in a certain way. And I have later on an example of why I want you to show your work in a certain way. It wouldn't be very clear with this one because this one's relatively straightforward. The first thing that should be jumping out at you, though, is, oh, look at that. It's the pi over 2 minus x. There's only one kind of identity that had the pi over 2 minus x, and that's our cofunction identities. So we know we're going to use the cofunction identities first. So, cofunction, just like the name sounds, the cofunction for cotangent is tangent. So I can rewrite that as tan x. But then we still have cosine x. So I've just rewritten the first identity, or the first factor, using as tangent x, using cofunction identities. So can I go further? I'm not sure. A lot of times, and this is just a strategy, and that's what tonight's homework is going to be, is giving you a lot of exposure to different strategies. A strategy that is often used is change everything to sine and cosine, because everything can be changed to sine and cosine using the quotient identities and the reciprocal identities. And so I can rewrite tangent as sine over cosine. Oh, and look, the cosines cancel. So the answer is that that original expression can simplify to sine x. If you were to actually put this into, words are so hard. If you were to put this into Desmos, you're going to see the graph of the original expression looks like the graph of sine. So it's kind of cool that way. So that's what we mean by simplify. Now, it's a little hard sometimes to know when you're fully simplified. But here's a general rule of thumb. But again, it's not a hard rule that you always know you're fully simplified when it looks like this. But a general rule of thumb is, if we can get it down to one trig function, let's do that. So if we can avoid using more than one trig function in the expression. Another thing, if you can get it down to a single fraction. Sometimes you'll start with multiple fractions, so you can get it down to a single fraction, a single term. That's usually preferred. Sometimes you'll have a choice between secant and cosine, or I should say like sine, tangent, and cosine, kind of like the three original ones, and then we have the reciprocals. If you can get it down to sine, cosine, and tangent, and avoid using secant, cosecant, and cotangent, that's usually preferred. The reason why I say usually is because, I mean, there actually is a purpose for doing this. An example is next year when you guys are in calculus. There's going to be types of problems that you can't do when they're written one way, but you use identities to rewrite the expression, and then you can do it. And you'll learn those strategies in calculus, but sometimes it will actually be more preferable to put a secant instead of a cosine. But sometimes you'll want the cosine instead of the secant. So it's hard to say a definite rule. It really depends on what you're going to do with this actually. But for this year, we're just practicing using the identities and rewriting stuff, so we don't really have a rule. But like I said, in general, single terms, preferable, and single, like using only one trig function is preferable. If you can avoid fractions, that's usually nice. If you can avoid using secant, cosecant, and cotangent, that's usually nice. Somebody's asking if they'll always use cofunction identities, and they won't. This one just happened to. Any questions on this one? And I'll give you one to try. So a lot of your homework is going to be kind of short like this. Some of it will be a little longer. Some of it will be short, though. Okay, here's one for you guys to try on your own. Try simplifying that, if you dare. Just kidding. Please dare. All right, so let's see what happens with this one. So again, you may not have thought about doing what I'm doing right here. Purpose of today is to give you exposure to different techniques and different strategies. So let's take a look at what happened. One strategy that is used a lot, like I said before, is if you're not sure what to do, change everything to terms of sines and cosines. So I use the reciprocal identity for cosecant, and I use the quotient identity for tangent, and then a reciprocal identity again. And oh, hey, that was cool. The first term, the signs cancel out. And then I was able to combine into a single fraction. So this one worked out nicely. Sometimes you'll have to find a common denominator. We started with two terms, but we were able to add the fractions together with a common denominator and get it down to a single term. And that's going to be another strategy that you'll see. It'll come up again today. And then here is an example of how do we know which one is actually more simplified? Because remember I said, if we can write it in terms of cosine, sine, and tangent, instead of secant, cosecant, and cotangent, that's usually preferred. However, this one had a fraction, and if we can avoid fractions, that's also usually preferred. So now we kind of have, wait, which one's better? This one's cosine, but it's a fraction. This one's secant, but it's no fraction. How do we know which one to use? And right now we don't. Just depends what we're going to do with it later. So I would have also accepted this because it's in terms of cosine. It's a fraction, but it's cosine, not secant. How do we know? Honestly, on a test, you'll actually see after the next section, 7.2, it'll be more clear how to put your answers. I'm going to leave it at that without getting into what the next section is. But for this section, if I gave you something like this on a test, it would be fine. If you're really not sure, wait, did I go far enough? Ask me in the chat, and I can tell you whether or not you went far enough. Now, the only danger with that, and this happens every year, if I give a quiz or something, somebody will come to me. They've already made a mistake, so they come to me with something and they say, is this an okay answer, or should I go further? And I tell them they should go further, and they go further correctly, but they've already made their mistake, and then they come back to me afterwards and say, you told me this was correct. And I was like, no, I never told you that your work was correct. I can't tell you that on a test, but I can tell you if you need to simplify further or not. So anyway, but any questions about this one? All right, let's look at another strategy. So sometimes, that did not come out right. Sometimes you have stuff like this. Now, the thing that I want you to notice, they gave us the problem, but just kind of get used to this one. What do you notice about these two factors? Anybody notice anything about them? I'll tell you there's a vocabulary word I'm using, a vocabulary word I'm looking for to describe these two factors. Anybody know what word I'm looking for? Yeah, Yojay's got it. Yeah. And the word I'm actually looking for is conjugates, but more important than the actual vocabulary word is what's put in there. It's the difference of squares formula, which Yojay gave us. So yay, both of you guys got this. That will actually be something handy. Let's see why. Let's see what happens with this. So remember, and I'm just going to go ahead and remind us of the formula that's up here. Remember when you multiply conjugates, I'll put it over here, a minus b times a plus b. Normally you would have to do the full, like multiplying every term together, blah, blah, blah. But your middle terms always cancel out, and it's just a squared minus b squared. We have a shortcut. So with this problem, I'm going to write down the original like I've been doing. Oh, my cat says hi. And then we're going to just use the formula. So we're going to have cotangent squared x minus cosecant squared x. Does anybody notice anything now? Very vague question, but anybody have an idea what we could do now? Exactly. Another general strategy, in general, like I said, I mean, these aren't hard rules, but in general, if you have functions that are squared, it's probably going to be involving the Pythagorean identities. Another thing that's indicating Pythagorean identities in this case is we do have one Pythagorean identity that relates cotangent and cosecant together. So that's another clue. So, we go back to our Pythagorean identities. So here we are right here at the end. And notice that, we have this form right here. Some people just memorize this form that I have highlighted. Some people memorize the others. I'll actually tell you with Pythagorean identities, here's what's most common. You have to have the three basic ones memorized. But a lot of people just jump for sine and cosine, because this is used so often. A lot of people just jump right into these. For the other ones, rather than using these four that I don't have highlighted as is, we still usually use the highlighted forms. It's just up to you. It's more to memorize, and so a lot of people don't. Oh, wait a minute, I'm going too far. No, I'm not. Where am I? There I am. So here's what I mean. That first form says 1 plus cotangent squared is cosecant squared. So it's already solved. That original form is already solved for cosecant squared. So I'm going to replace the cosecant squared with what it equals. And then, well, look at that. Our cotangent squareds are going to cancel. And we're going to be left with -1. I would say that's definitely as simple as we can get. This one's pretty clear what its actual final answer is. Somebody's asking if there's a Quizlet for these identities, and yes, there is. Back in that module 6, I'll copy all that stuff over to this new module, but between now and when I get a chance to, if you go back to the Unit 6 module, when I put the Quizlet identities in, or the Quizlets in there was one for the identities. All right, any questions about that one? Pretty straightforward. Because here's one for you to try. Ooh, see if you can factor that one. I'll give you a hint. Actually, I won't give you a hint, but can somebody give us a hint? Can somebody say in one word what factoring strategy you think we're going to use on this one? Don't give anything away except just the factoring strategy. Yes, excellent. This is going to be a grouping problem. Yeah. So, Momo, cubes is not a bad idea because of the cubed, but remember sum of cubes and difference of cubes only had 2 terms. So, but good thinking on that. So somebody wanted to know on the test, will I take off points for not being fully simplified? And yes, I will. If you're not fully simplified, I will take off points. All right, let's see. So first of all, do not try to write what I just have down. But I want you to take a look at what I have down. What a hot mess that is, huh? Remember how in the beginning I said I want you to format your work a certain way? And I'll show you later why. Because I often get stuff that looks like this. Now when I show you the way I want you to write your answers down, it will have exactly the same thing I have written down here. Now this is done correctly, so it's not as bad to read, but what a hot mess it is. Please don't do this to me. What I am asking for is 2 things that were not done on that previous example. First of all, spaces in between your lines. Give me a little bit of gap, please. I know it uses more paper, but when you cram everything together, especially when the problems get longer like this one, and when there's fractions on some lines but not fractions on others, It really is hard to read. And if you've made a mistake somewhere, then I'm trying to read your mistake to try to figure out, was it a tiny little mistake? Do you just lose a little bit? Or is it a major mistake? Anyway, leave a little gap in between your lines. It's very helpful. The other thing is, notice the equal signs. The equal signs also help identify the start of a line. Let me go back up here real quick. Now, I'm not saying do this, but if I had just put equal signs centered at the start of each line, it actually, just that little tiny bit alone helps make it easier. I know there's actually some math teachers that don't want equal signs. So I know this is totally a personal preference. But over the years, I've just found it much easier for me to grade when it's like this. So when you're dealing with simplifying trig identities, one technique that's used, you write the original on one side, and then on the other side is all your work. Equals this, equals that, equals this, equals that, equals this. I am asking you, please show your work like this. So much easier for me to grade, so much easier for me to find your work. Now, the next thing I wanted to point out on this, notice I haven't boxed anything, because this is a good example. I mean, I got here, that looks pretty darn good, but it definitely has multiple, but technically I guess it's a single term, but we got these two factors. It just seems like we should be able to go further. So let's see here, I distributed, I got here, I changed everything in terms of sine and cosine. I had two fractions. I found a common denominator and simplified it down to one fraction. I am not getting anywhere. Now I've got a cubed down there. This, sure, it's got sine squared. Maybe I could use a Pythagorean identity, but it just doesn't seem like I'm getting anywhere, does it? And that happens sometimes. It turns out that really this is about as simple as you can get. All of this got me nowhere. Here, actually, I'm pointing to all of this. This really got us nowhere. So, in case you were one of those, I'd also try to go further and to see what would happen. And you found I don't seem to be getting anywhere. It's because, yeah, this is one of those where sometimes it gets a little vague on when am I simplified. But I was just making it even messier here. Any questions on this one? I'll be honest with you, I probably wouldn't give you one as vague as this on a test, just because it really is, when are we finally simplified? This one really is very vague. Oh, because it shouldn't have. Thanks. You are correct. I don't know why I was thinking that. Let's see, I'm pretty sure this won't get us anywhere still. Yeah, so now I'll have a sine squared x up there. Yeah, so we're still not getting anywhere. But thanks, you are correct. Somebody's wondering how I got secant x tan squared x. I distributed. So at, let's see here, this line, if we were to distribute the tan squared to both terms, secant times tan squared is secant times tan squared. Any other questions? All right. I'm actually going to skip a couple of these. Let's look at this one. And if we have time, we'll come back to the other one. The other one was just subtracting. We've already kind of looked at that, getting a common denominator. Like I said, we'll come back to that one if we have time. But this is a totally different kind of problem, but it's still using our identities, and you are going to have some of these on homework. So let's just look at it, because what the heck is it asking? It's actually very straightforward. It says use trig substitution to write the algebraic function as a trig function of theta with theta between 0 and pi over 2. What? Just do what it says. It says use trig substitution, and you may be going, well, what does that mean? It just means substitute with trig. And they're telling you what to actually substitute. In this case, they're saying let x equal 2 cosine theta. So I'm just going to rewrite this and let x equal 2 cosine theta and see where that takes us. So we are going to start with this. The square root of 64 minus 16x squared, that was given. And we are going to substitute the x with 2 cosine theta. Oh, but it's x squared, so 2 cosine theta should get squared. Oh, this seems weird, but we'll go with it. So 2 cosine theta squared is going to be 4 cosine squared theta. Still multiplied by 16 though. And 16 times 4 is 64. Ah, but I do have a 64 that I can factor out. So if I factor out the 64, then I'm left with 1 minus cosine squared theta. Now since everything was in a radical, I'm going to have both of those factors still in a radical. What can I do with that 1 minus cosine squared theta? It does, you are right. And lo and behold, I can take the square root of both of these, and I just get 8 sine theta. And they did tell us theta's in quadrant 1, so we know to keep everything positive. And this is actually a strategy that's used in calculus a lot. You'll start with an expression like this, which is a little harder to work with, and then you get it down to 8 sine theta. Maybe you changed variables, but again, that's a strategy we also use in calculus. But 8 sine theta is a lot easier to work with than the square root of 64 minus 16x squared. And somebody's wondering where I got the 64 and 16 from. I'm not sure which 64 you... Remember, the purple is what we were given. So I try to color code the original problem with my work. So we were given the purple stuff in the beginning. And here, I'll make it very clear. I'll put the word given. So that might take care of the question. Oh, okay, it looks like that. So here's one for you guys to try. And again, you're going to have a problem like this on your homework. It's very similar, it just asks you to go a tiny bit further. All right, so let's see what this one was asking. Like I said, it was pretty much the same, just wanted us to go a little further. I can barely fit it. I'll fit the important stuff. So we start off the same though. You know, it gave you an expression and it told us what to let x equal. So I let x equal that thing. By the way, I just want to point this out again. This time I didn't put the equal signs, which if I had done what I asked you guys to do, I should have. But notice even just having the gaps in between, I can still see one line from the next. So again, please. I got down to here. Now this one was a little different than the previous problem because it actually was an equation. So I actually not only was able to simplify the right side to 10 sine theta, but I know what it equals. So the problem did say then find sine theta and cosine theta. So if I just solve for sine theta, divide both sides by 10, I get this. And now I have sine theta. That was one of the things that they asked us for, so that's why I boxed it. But from that, based on what we did in the last unit, we know that that theta can be negative pi over 3. And then we can take the cosine of that angle. And negative pi over 3 would be in quadrant 4, where cosine's positive. So it's a positive 1/2. And that answers the other part of the question. So just a tiny bit further than the previous problem, but don't get thrown off when the problem asks you that. It's very similar to the previous one. So any questions about this one? Just super quick, the problem that we skipped, just to let you see, it does say to subtract and then simplify. So this is one of those examples. A lot of times when you have multiple terms, we'll try to get it to a single fraction using a common denominator. Now I could have changed all of this to sine and cosine, but with this guy already being a fraction, I would have fractions within fractions. That's what made me avoid that. Because I didn't want to have 1 over cosine squared over sine over cos. Like, that just seems awful. But I could get a common denominator of tangent. If I multiply top and bottom of this one by tangent, now I have a common denominator, and I can combine the top together. And this is that numerator now is very similar to the previous example we did. I can use Pythagorean identities to rewrite secant squared, and then the tangent squareds cancel out, and then I can just have it as a negative cotangent. It kind of fell into place very nicely. So, any questions on any of this? And yes, I will have this posted after class. It'll take a little, like a few minutes for the video to render, so it won't go up immediately after class, but it will definitely go up before the start of the next period. Any questions at all? It is 10:10. It is time for you guys to go. So if you want to take off, feel free. Otherwise, I will see you guys on Thursday. I have study hall next period too if anybody wants to come over to study hall. Bye, y'all.